Good afternoon, everybody. I'd like to start by thanking the organizers. It's always a pleasure to be Illuminee. So thank you for putting this together, and thank you for inviting me. So the topic of this talk will be on linear algebra for large language models. And I started looking at machine learning a few years back because I'm in computer science department, and I have students who are really interested mostly in machine learning. They don't want to do numeric analysis. They don't want to hear about mathematics or anything like that. So I have to adapt. And during a recent visit to QCRI in Qatar, I talked with a former student by the name of Abdelkader Bagag, and we challenged each other to write a paper on essentially numeric algebra for large language models with the goal of essentially explaining what is going on in that field with linear algebra viewpoint and terminology. I also have some collaboration for some years with Yuan Shi, who is a professor now at Emory, who was a postdoc with me at some point. And we have some work on acceleration type techniques for machine learning in general, but also for other things. And you'll see some of the names listed later. This work is supported by NSF. So the plan is first a little bit of a non-technical part on just AI in general and what's happening in the field. And then I will talk a little bit about some details of LLMs. And later on, towards the end, I will talk about some ideas on how to adapt acceleration techniques for these sort of large language models, or actually for just deep learning. So the rise and impact of machine learning. Just a brief review of what's happened in the past. People started looking at data mining a few years back with the idea of extracting data from extracting information from data. For example, things like clustering, embedding, and supervised learning in general, network analysis, PageRank, ideas of centrality, all of these things were part of data mining. And there's actually a lot of linear algebra in these topics. Then there was a huge push on classification type techniques, linear discriminant analysis, support vector machines, and so on. These are all geared towards classification. For example, classifying an email as spam or non-spam and things like that. Okay. Later about in the 2010s, there was a revival of neural networks, which was a topic that was started in the 90s, actually even before that, but it had a big push in the 90s, and then it died out. And then in the 2010s, people started looking at it again. And then this was mainly for classification. Then people looked at deep neural networks. So these are neural networks in many, many layers. And this was extended to what we now know as large language models and so on. If you want a good reading on this, what has happened in recent years, this is a good recommendation that I have. It's actually a nice book to read. It's also a little bit concerning when you read the book. Most of the book was about containment. How do you make sure that this does not go badly used or astray, essentially? But what he was saying is that there's a lot of progress that has been done astounding progress is the word he uses, in the last 6 and 7 years. And I would say that people who were authors of these things were themselves surprised by the results. It was really amazing when you read what has happened. We'll see it later on, what I mean by that. So I made a little comparison with Moore's law. Moore's law stipulated in the 1960s, mid-60s, that the number of transistors you can place in a chip doubles every 2 years, sorry. And that was consistently true for decades after that. It only started to be questioned in recent years. And you could ask whether there is something similar for AI or for deep learning or things that have to do with artificial intelligence. So technology progresses in exponential bursts. When everybody gets into the technology, there are developments happening quickly, and that's what you see. In here, what I have is this chart, which is a well-known chart on the transistor of the chips that have been fabricated starting with the 70s. And you can see here the number of chips is listed, the number of transistors is listed on the left side. We're reaching the tens of billions now in little things like this. It's amazing what it's done. And but this has taken, 5 decades essentially, right? And you could see, we could ask this question, what are we seeing in AI? And I did something very simple, a little crude for now because I don't have that many points. They started in 2018 with, I think, in this case, with just the point that I'm showing here is probably BERT, one of the LLMs. And they have only 5 points, and I put this plot, and you can see it's a little bit of a very similar exponential curve. This is a logarithmic scale, obviously. And the thing that you observe is that the doubling does not count in years, but in months. It's 4.3 months. You get a doubling every 4.3 months. It's about a factor of 10 every 14 months. So it's very, very fast, but I have to say that it's probably not sustainable, right? Because we're reaching here's the number of parameters for the latest one. It's an estimate. 100 trillion parameters that's used in GPT-4. And I will show you for GPT-3 actually how you count these parameters. Okay. So that is rather remarkable. This is showing the parameters. I don't show the data, the amount of data that's being used, because that's not available. It's they have what they call a corpus of data, which is enormous. And these sort of simulations don't take days; they take months. Okay, on big machines. So I tell you, it doesn't have anything to do with the kind of things we're used to with scientific computing. So AI is very disruptive. Students are only interested in AI-related work, in part because the traditional jobs are no longer there; they're disappearing. If you don't say data science, machine learning, AI, if you don't put that in your CV, chances of getting a job are this slim. I shouldn't be so negative for students. Don't be discouraged. It's not too bad. On the education side, there's also a big disruption because you cannot teach the same way we used to teach. Homeworks can be now dealt with ChatGPT-4. And so a faculty member in our department 3 years ago, or 2 years ago, said, well, we shouldn't be concerned about AI. It's not doing much. I did this test and it's okay. We can. And he came back last year and he said, there is a problem. So I was very surprised by that. He had to give it an exam, and he just took the picture of the exam, not even typing it, just took it and projected it and said, give me a solution. This is a robotics, there is a picture in there. It's just looking at it was not trivial. And he said, I was very surprised by the first answers, but the thing that was very, very surprising to him was that there was one part was extremely creative. That was also solved. That was truly, he said, it's really a problem. So now if you get GPT-4, you could use that easily. It's really amazing. I actually have to tell you, and I'm using it myself for some things. At the end, I will tell you about that, but it's really interesting. So the danger is, can numerical algebra become irrelevant? In fact, I point you to the fact that grants or research support in this area, in these traditional areas, are disappearing a little bit. I know it's the case in the US. So a lot of the money is going now into AI-related work. But I think if you want to do numerical algebra, we have to reconsider what we're doing. The reasonable goal is to still do some traditional work, but also to try to participate in deep learning research. I have a difficulty with some things in this because there is a very big difference in culture. Things are very fast-paced, and it's very, very different. And I think there's some negative things about negative aspects to this. I think some of you may know if you have tried to publish something in this area, it's not entirely we're used to a very nice environment in numerical algebra, right? It's really good, you know. I think in other areas, it's really cutthroat. It's very bad. In some areas, it's pretty bad. Okay, so, next thing I will talk about is, I will give you some details about large language models, and bear in mind, we're still discovering this as we go. So some of this stuff is really to tell you what the main pieces are. So let's start with deep neural network. This is the multi-layer perceptron is at the heart of these large language models. So you can explain it very easily. What is it? It's simply, you can think of it as approximating a function, okay, which is given by a sort of algorithm like this. So you have an x, and the output is y. These are vectors, right? And it starts with some z0 equals x, and you have a transformation that looks like this at every stage. And you have here L+1 stages. These are the stages represented here. This is the input stage, input layer. This is the output layer. This is the final y. And these are what is called the hidden layers. So what it does is it takes the previous z, multiplies it by a certain matrix W, and adds a bias. And then there's a function here, which is called an activation function. It's a very simple function which is applied to all of the components. And that function is nonlinear. So if you remove that nonlinear function, then everything is just a linear transformation. It's just a matrix product. And what are we trying to do? We're trying to find the best W and the best B, best WLs and the best BLs, such that at the output, your Y matches some data. So phi of x is equal to some Y hat. It could be, for example, digits. Imagine you have samples of digits, many samples, and you have this function that it gets you from one image to a number between 0 and 9. Okay, it tells that's essentially what this does. So, and then you have a lot of this data that is stored, and you find the best possible weights that match the input to the output. So the output you get in the end to the given data that you have. That's called training. So when you find the W's and B's, then you get training. And then when you have a new digit that comes in and when you identify it, just apply the same routine and you can find the corresponding output, the corresponding digit associated with the data. In the past, we had different methods, and I had an intern at one point, an undergraduate student, who tried this. This is about maybe 8 or 9 years ago. And he tried these methods against the other methods, traditional methods we were trying. These are things very simple like PCA and doing reduction, doing all sorts of some very sophisticated methods. But these are infinitely better. They're incredibly accurate. You know, you can get 100% accuracy for some simple data. I'll show you that later. So that's the first ingredient. This is called multi-layer perceptron, and you can have a number of layers here, which could be large. In fact, deep neural networks will have many of these layers in between. Okay. So the problem is not convex, but it's highly parameterized because you have a lot of parameters if you have many layers. The training is very expensive. And then, sorry, I went too fast here. Okay, no, I was going to pass them backwards. Okay, I am confused. Okay, so then starting in 2017, there was a huge development, and that I'm going to talk about in a second. And these are some of the early versions of GPT and large language models, and now we have a new one. One that came out very recently is Llama by Meta, and there are quite a few. There's lots of them now that are being developed. There are different ones in different languages and so on. How are these methods optimized? They're optimized by simple techniques. Gradient descent type ideas, as you can see here. Okay, so I am looking at the gradient descent here. What you do instead of using something like this is you observe the fact that f is some average of several functions. The typical function f in AI is like this. And so instead of using this entire average, what you do instead is take bunches of them. These are called mini batches. And you keep selecting a small number of a bunch, which is, for example, 20 of these functions, okay, at random. And then you do an optimizing with that, and then you get to the next one, and next one. So you never use the whole set at the same time. So this is called stochastic gradient descent, and it's really at the heart of optimization in deep learning. Even the other methods use something similar. They use things like, batches. So these are, ADAM is actually one of the best known ones, and RMS prep, and there are other ones here. But keep in mind, this is what we have in mind. Just look at stochastic gradient descent, which is a form of gradient descent, where instead of using the whole gradient, you take a few at a time and you average them out. And those are selected at random, and you keep repeating. That's all there is to it. Okay, so let's give you the other ingredient that's used in large language models, and that's the idea of attention. So I'll give you a very simple example here. Suppose you want to find a function f, right? You're given data. You're given data points, xi and yi, as you can see here. These are data points. And you want to find a function f. In numerical analysis, the way you solve this problem is simply, you know that it's noisy, so you take least squares. So you take interpolation in the least square sense, right? So you take, for example, you say that function is a cubic polynomial, and you try to match the data that you have, x as well as in the square sense. Okay, that's a very simple one, interpolation or, okay. So in machine learning, they do it completely differently. You use the data points and you do some sort of averaging of the yi's. Here's what happens. So the terminology that's used here is from databases. You have a ki, these are keys. VI's are values. These are nothing but our xi's and yi's. So these are the points that were given, the dots I had earlier. And you have a query Q, since it's an x, at which I want to find f of x. That's called the query. So you have K, V, and Q. Very common terminology. And to find the function, to find the value at Q, what I would do is average out the yi's, what I call yi's, but in MI, in AI, they're called VI's. I average them out, and in order to average them out, I use a kernel, which is the kernel that you see here. So it's a function of two vectors, and then this is my result. Would be A of Q would be the kernel sort of averaging the value of VI's using the kernel. Okay, so in fact, in this case, you'll find that I don't have a curve here. But you see that the ML-based approach is very accurate in a sense. It goes, yeah, okay. So next thing, I will talk a little bit about the transformers. So this is the idea behind LLMs. So what in the past, what people did was to use, I'm sorry. Okay, so these techniques that were used in the past, material perceptron, and there's CNN and so on, we're having a problem with the fact that if you want to deal with a sequence, then you have to capture that sequence, the nature of that sequence. And what the problem is that the methods that were developed were having some instabilities, and they're trying to fix them. It was really a mess until this paper came. In 2017, attention is all you need. There was really a major breakthrough. That's how things are done now. This is what caused this big progress, big jump in LLMs. So what this does is essentially use attention, the thing that I talked about, and then adding positional encoding to take care of the sequencing. So this is details you can see. So this is now getting some details about LLMs. So the very first step that is done in this model, in these techniques, is to transform the sequences in words, whatever, into tokens, and then those are embedded into vectors. So you go from words, and then you get tokens, which is just numbers, indices. word number 1, number 25, etc. And then you embed that using embedding techniques into vectors. So now we're in friendly territory, or in linear algebra territory, okay? That's, everything goes through that. You go through vectors, embedding, okay. And then you transform your, so these are, you get with the big matrix x0, which is n, which is the number of tokens you have, and d, which is dimension, the embedding dimension. For example, in ChatGPT, this would be 12,288. Okay, so, and then you transform those, and you get some result here, and then there's it gives you, you go into a cost function, and this is how you decide on the optimizing. So these are the main 3 steps. This is multi-headed attention. This is linear normalization, and there are blocks. There are hundreds of these blocks. Okay, and then the L corresponds to the blocks. And then the MLP is here, and then this is another transformation at the end, which is called residual attention. Residual. So here's actually, I'm going to show you this slide and then move on. So here's another way to write it. Every AI is considered as a row. You're treating these rows. And this is the multi-headed attention I talked about earlier, which is all the previous rows. And then this is MLP, and then you go to the next step. Look at this particular MLP here. You see you have a function that's like the sigma we had before, which is called normalization, and we have W matrix here exactly like we had before. You have 2 of these. You have 2 layers in here, okay? And let's look at what happens in ChatGPT 3 in terms of the number of variables. So go back here. I'm going to look specifically at this layer, the MLP part. So you have this matrix. You have, I'm going to ignore this part. It's small compared to this. This is variable, 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 variable. And you have L, which is the number, L corresponds to the block. So here are some details. Embedding dimension, I just mentioned that earlier. This is a side when you do the embedding to tokens to vector space, that's a dimension, 12,288. In MLP, these things are of size, they decided it would be, number of rows would be 4 times embedding, and then times the embedding. The dimension of embedding is always the same. And then you see the matrix size, you can see here, the square of this, which is roughly 4 times 1.5 10 to the power 8. And then that each of these will be 6 times 8 to the power 8, right? So you multiply this, so this is, each of them would be that. I multiply this by the number of blocks, which is 96, okay? In GPT-3, you have 96 blocks. They have 96 heads as well in the multi-head. So that gives you 120 billion. Just that gives you 120 billion. And if you look at the MHA, very similar count will give you 54 billion, and there are a couple of other things. And that you get easily to 175 billion, okay? In Llama, they have 450 billion parameters. Okay, so where is the linear algebra? Which linear algebra tools can help? So you have really to go into the different boxes to see where to find answers. I'll give you a couple of examples just to illustrate this. One example is the linear algebra used in the attention. So in attention, you compute something like this. This is a matrix that you can see here. This is another matrix, and this is essentially in ChatGPT-3, this would be 12,288, and this would be 120. And then this is a nonlinear function of this matrix, which would be a square matrix here, multiplied by this matrix V, okay? So the problem is you have to compute this first and then multiply by V. If this were linear, if you didn't have this, you would not do it that way, right? You compute first the Q transpose times V, and then the result times Q. That would be infinitely, a lot cheaper, right? Doing it that way. So the idea they had is to say, let's replace this function by a product of functions like these. Now that really was a very simple idea. that had huge impact, was much less expensive to compute it this way than just computing this whole block and then multiplying it by V. So this is a very simple idea. Another idea is known as LoRa, and this is something that also had a big impact, and that's really essentially exploiting the fact that in deep learning, you have the parameters tend to be of low dimension. So what you do is when you have a first training, you have the matrix W, some weight matrix W, you fix that and you add a low rank matrix to it, and that's what's trained. This one is not trained, so this is much cheaper. So there are a lot of papers based on this stuff. So I'm going to say just a few words on acceleration type techniques. I think some people talked about RRE yesterday, and what I will do is look at methods on these two things here, extrapolation and then fixed point acceleration techniques, and there are a lot of methods that we're working on. But I'll essentially look at these three ideas. RRE, where RRE is based on essentially extrapolating a linear mapping like this, and then you say that now you just consider the xj's to be coming from something like this. They may not be, but you just consider that, and then you extrapolate. What we do here is you restart. You do exactly that extrapolation and the restart, and then you add. We do something similar to what's done in Anderson. You add beta times some residual, which is linear residual, and then you restart the process. Anderson is similar, but you restart at every step, essentially. And then we have a recent method here, which does essentially Anderson with truncated Gram-Schmidt, which is a version of Anderson, which does which has the advantage that it gives you a three-term recurrence. It's somewhat interesting, yeah. So general observations are the following. The second-order type methods do not work very well because they rely on smoothness. We don't have smoothness. Things change over time. So what we did is to keep the same batch for the acceleration. We use a small dimension for restarting, and that the baseline here is SGD. We're trying to use SGD stochastic gradient as a baseline and try to accelerate that. And the experiment I did here was where we just eminist with 2,000 images. It's a very small set, and you could do that. And here are some results. The point is not to show you the results. You can accelerate. Essentially, the main point is you can accelerate these sort of things by being a little more careful that things are stochastic. You want to make sure that there's some smoothness in the process and so on. And here you see here that ATGS worked quite well, but for the second example, you have some oscillations, and that has to do with some stability issues. We know about this. That's illustrated in the paper. The reason I want to show this experiment is not for the experiment itself. Is because I did this myself, and I forced myself to learn PyTorch, and I could not have done it without ChatGPT. This is really amazing. You go there and ask, write me, how do you write the code to do this? And then I don't understand that. The answers, it's your teacher. So we need to pay attention to what's going on, but you have to get inside the course to be able to contribute to this thing. And ChatGPT is our new teacher. PyTorch is our new math lab, okay? The world has changed, really. And the methods we use for research and for teaching and for learning also must change. This is definitely going to be the case. We'll see that more and more now in the future. So I leave you with this question here at the end. Not entirely clear what the answer is. So I'm going to stop here and answer questions.